All right, good morning. This is your stat sensei, Mr. Spensei, and we're going to do the last and final scenario for our review. So, investigators at the U.S. Department of Agriculture wish to compare methods of determining the level of E. coli bacteria contamination in beef. Two different methods, A and B, of determining the level of contamination were used for each of 10 randomly selected specimens of a certain type of beef. All right, so we know our sample size. We have 10. And um, from more than 1,000. Wow, looks like that might be our population of contaminated meat. Those differences are normally distributed. That's good to know for conditions purposes. The data obtained in millimicrobes per liter of ground beef for each of the methods are shown below in the table. And it says construct a 90% confidence interval. Well, notice we have 10 different readings. I mean, we have 10 different numbers, but we have 20 readings. Why? Each one was tested twice. That lets me know we have paired data. In the previous video, we checked our stat calc to make sure that we had our data entered into the calculator correctly. So I'm not going to go through that again. But I am going to rewrite my parameter because we are going to be referring to it in our conclusions. So let mu d equal the true population mean of the differences in detection and it's going to be method A minus B. All right, so we're not going to do our conclusions. We did them previously in the previous video, so I'm not going to restate them on a AP exam. You would, but here we're not going to redo it since we've already done it. So X bar plus or minus T star S divided by the square root of N. And some of you are already saying, hey, he didn't do something. Well, this is my standard form, but I need to drop a couple D's on it for because it is a paired, and that shows the differences, the sample mean of the differences, the standard deviation of the differences. So X equals, well, what did X bar equal? The quickest and fastest way is just go stat test and drop down to T interval. Data needs to be L3, and we're running a 90% interval, so 0.90. And I find out that my X bar is 0.29. I also find out my standard deviation is 0.6297. We have a sample size of 10, and we have a confidence level of 0.90. Now, alternatively, I could have gotten the same information by going stat, calc, one var stat, and gone to L3. And you can see that there's 0.29 and there's a 0.6297. All right, so degrees of freedom. Degrees of freedom are simply going to be 10 minus 1. We need to calculate T star. So we're going to have to go inverse T is where we're going to go to. And it's going to ask us for our area. And our area is going to be 1 minus 0.90 divided by 2. And now we'll get our T star for us. So second vars, inverse T, parenthesis 1 minus 0.90, close parenthesis, divided by 2. And I end up getting 1.7530. We're going to make that positive because of the positive people that we are. Actually, there's a longer explanation, but we're going to leave that off. We're going to go ahead and plug in. So our X bar, plugging into this formula, our X bar is 0.29 plus or minus T star, we just calculated as 1.7530. And then we have S of 0.6297. And we have a sample of size 10 that we're going to take the square root of. All right, let's actually write this. Let's go actually run this and calculate it. So stat test T interval. Once again, data is highlighted. We're in column L3, 90%. And there's our interval. Now, one thing that's really important to note is our interval contains zero. The fact that it contains zero means I don't have a statistically significant difference. Yes, we ended up with a difference, but it's not statistically significant. It could have happened by random chance alone. All right, so there's my lower bound and there's my upper bound. So we are 90% confident that the true population mean of the differences in detection, method A minus B, lies within the interval negative 0.075 to 0.655. Now, if I notice, one thing I notice is 0.655 is farther away from zero than negative 0.75, which means A was slightly higher. All right, it means A was higher than B, but it wasn't statistically significant. Also, please remember this right here, the true population mean of the differences, the detection method is just a restatement of our parameter. All right, so the meaning, when I have the word meaning, all I'm talking about is explain what the confidence level means in context. So in context, if we did this over and over again, so I like to say in repeated sampling, we expect this method. This is kind of our brag. It's so good that we expect this method to work how often? Well, we expect it to capture the true population mean of the differences in detection method A minus B. Well, how often do we expect it to work? We expect it to work 90% of the time. So if I did it over and over again, I'm not 90% sure I'll get this interval, but I'm 90% sure that the interval that I do get actually contains the true population mean. That also means that if I did this over and over again, 10% of the time, I wouldn't capture it. It would be outside of that interval. Could have been higher, could have been lower, but it wouldn't have been in that interval 10%, or we would not have captured it 10% of the time. Doesn't mean that I'm 90% sure this interval is correct. It just means that if I did it over and over again, 90% of the time, we would capture it. And I'm 90% confident that within that interval is the true population mean. All right. Well, I sure appreciate you watching and I hope to see you on the next one. Thank you.